Hello, everyone. All right. It's Thursday. That means it's webinar day. I hope you're excited. I certainly am. And how do I spotlight? What does spotlight mean? Right. So yes, today we're going to do complex numbers. I have prepared 6 questions for you for complex numbers. The questions can be accessed here. I will also be showing them on the screen as we go along. And here's a link to the whiteboard. Nope. Here's a link to the whiteboard. And here's a link to the previous webinar on complex numbers, right? Because we've already done a webinar on complex numbers. You might want to go through that because the questions are slightly more similar to the assignments. So yeah, so today I'm going to go through quite straightforward questions. And maybe we'll have some time left for the tricky ones. So yes, this is recorded. If you need to go, of course, I hope everything is okay. Right. Oh. I've made a mistake. Okay. Can view. Can I please ask you to close iDrew and then open the link again? Can you please do that? 2 more people are still on one person is still on iDrew. Can you please close the window and reopen it? Thank you. Thank you very much. Okay, so now you can have a look. Now you can see what's going on. These are saved, so you can access the materials from last week, and of course the materials from this week. Okay, so let's get to it. So let's dive into some complex numbers. Who has done complex numbers in school? Type 1 if you have done complex numbers in school. Oh, okay, so quite a few of you. Okay, so you'll be familiar with some of the things we do, and maybe all of the things we do. I don't know. So, but hopefully this still will be useful for you because I can't say I'm going to do just the basics. No, I'm going to start with the basics and then we'll go into a little bit deeper. We won't do transformations today. So so what are we doing? We're doing just writing numbers in different form. Then we'll do a simultaneous equation. Then we will do some taking complex numbers to the power of. You could actually use binomial expansion here. I haven't realized that, but yeah, there are other ways to do this. And so finding the roots, so complex roots, that's a very interesting topic. And we're going to solve a quadratic equation with complex coefficients. And finally, we will do some Argand diagrams. We will sketch some regions that satisfy. So this is the plan for today. So yes, I hope. Is there anyone here who knows how to do every single question from today? Anyone here who knows how to do? Okay, possibly. All right. And even the roots, like finding the fourth root of -1. Do you know how to do this one? Well, possibly. Roots of unity. Yes, that is. These are roots of unity. Well, we won't call them roots of unity because they are just roots. All right. Okay. So write the numbers in trigonometric form and in polar form. So just a reminder for you. So a trigonometric form. So a complex number. Okay, so let's start with a complex number. A complex number is a number in the form x plus iy is a complex number. Complex, where x and y are real numbers. And I has a special meaning that I squared is -1. Okay, I squared is -1. It's called the imaginary one. So I is the imaginary one. And complex numbers can be represented on an Argand diagram. So for example, if you have x plus iy, you can have a complex number, and which can be placed on a diagram. So this is x, this is iy. So this is the real axis, this is the complex axis. So 2 minus 2i, this is a number that can be written here. So it's 2, 1, 2, minus 2i, minus 2. So that's 2, that's minus 2i. So this number is 2 minus 2i. Okay. And if you measure the angle from the positive x-axis, so if you measure the angle to this, so this is like a vector. So it's a vector representation of a complex number, where x is the x coordinate and y is the y coordinate. So 2 minus 2. That's a vector 2 minus 2. And if you find this angle, you can write, so this angle is 7 pi over 4. 7 pi over 4. There is the trigonometric form. Trigonometric form. It's modulus of z. So it's the modulus is the length of the vector. Modulus of z multiplied by cosine of the angle plus I sine of the angle. So a number z, the complex number z, can be represented in trigonometric form. And in modulus argument form, or exponential form, modulus argument form, we can write it as z equal modulus of z multiplied by e I theta. Okay, so just let's make it straightforward. So we have a number z. It's a complex number. Z equals x plus iy. And if we draw a vector from the origin, the length of this vector is known as the modulus of the complex number z. And this angle, theta, is known as the argument. So z, modulus z, is the modulus of z. And this is argument argument of z. So it's we can write it as arg z and modulus z. Okay. So basically, any complex number can be written as modulus e I theta. But it also can be written in trigonometric form, which is here. Okay. Have I confused anyone? Is there anyone here who has no idea what I'm talking about? Or is how EI no idea about EI theta? Well, there is the Euler's identity that EI theta is equal to cos theta plus I sine theta. Let's just believe this to be true for now. This is the Euler's identity. And so yes, if you have a complex number, well, okay, let's it is related. So let's have a look. So we have the x-axis. Maybe I should have started with the basics, x, y. And you have a complex number. A complex number has x and y. So let's make it simple. This is a complex number, x plus iy. So this is x, this is iy, or just y. I mean, depends on how you look at it. It's the same thing. It doesn't really matter how you put it. And here you can say that this length, so if this is modulus z, this is modulus z, and this is theta, you can say that x is equal to modulus z cos theta, right? That's how we resolve vectors. It's like the horizontal component of the vector. And the y component of the vector is modulus z sine theta. So we can rewrite this. So using this, we can write x plus iy is equal to z modulus z cos theta plus I modulus z sine theta. And we can factor z out, cos theta plus I theta, I sine theta, sine theta. Does that make sense now? Does that make sense now? Does the trigonometric one make sense? So whoever said that does make sense. Now, and then we have the Euler's identity. So EI theta is equal to cos theta plus I sine theta. So yeah, so let's believe this to be true, because I'd love to go through the derivation of this, but I don't want to spend a lot of time. So yes, and that means you can replace this with simply e to the power I theta. Therefore, this is equal to modulus Z E I theta. And this is called the modulus argument form. Well, this is also called the modulus argument form. So, for example, let's make a for instance. The complex number 3 plus 3i. Yeah, that's the complex number that is here. We know the length. What's the length of this vector? So z equals 3 plus 3i. What's the modulus of this complex number? 3 root 2. Yes, it is from the Maclaurin expansion. That's one way of doing it. So modulus z equals 3 root 2. And then the argument, the theta, is the argument of z, which is arg z. What's the angle? 45. Well, we do pi over 4. Pi over 4. Therefore, z, which is 3 root plus root 3i, can be also written as 3 root 2, open bracket, cos pi over 4 plus I sine pi over 4. And you can check this to be true if you just expand, because cos pi over 4 is root 2 over 2. And sine pi over 4 is also root 2 over 2. And if you open the brackets, you get 3 plus 3i. But you can also write it as 3 root 2 e to the power I pi over 4. So these are 3 different ways to write down complex numbers. So this is called the Cartesian. This is called trigonometric. This is sometimes called exponential, or I call it modulus argument form. Modulus argument. It's just sometimes this one is called modulus argument because technically it does have modulus and argument, but different people call it differently. Okay, so right. Arose by any other name. That's the great one said, it doesn't matter how you call it, as long as you understand what it is. Right, so let's do this one. 2 minus 2i. So 2 minus 2i. So the easiest way to do this is to draw. So 2, so that's 1, 2. Minus 2i, so 1, 2. Okay, so this is 2 minus 2i. So this is question 1. 2 minus 2i. And you can see that the angle. Now, previously, I said the angle is 7 pi over 4. Well, I don't have to go that way. I could go this way. I could go minus pi over 4. Right? So the argument is minus pi over 4. So modulus of z is 2 root 2. And argument of z is minus pi over 4. So z can be written as 2 root 2, open bracket, cos minus pi over 4 plus I sine pi over 4, minus pi over 4. And now we remember that cosine is an even function. Cosine is even, and that means cos minus x is equal to cos x. Therefore, it's 2 root 2, open bracket, cos pi over 4. We don't need the minus. And then we remember that sine is an odd function. Sine minus x is minus sine x. And therefore, sine minus pi over 4 is minus sine pi over 4. So it's minus I sine pi over 4. This is how you can write it. And of course, it could be written as 2 root 2 e minus pi over 4I. Okay. Happy with that? How well do you understand the first task? The second one's going to be easier, actually. How well do you understand the first task? On a scale of 0 to 10, please. 10s are always the fastest. Anything other than 10? Everything's clear. All right. Okay, that's good. So okay, let's just skim through it. So number 2 is -1. So modulus of -1 is 1, and argument of -1 is pi, because if you think about it, -1 is here, so this is 0, this is -1, so the angle is pi. Therefore, you can very quickly write that -1, so hence -1 is modulus of z, which is 1, multiplied, open bracket, cos pi plus I sine pi. Now, it looks like a very complicated way of writing -1, but we will use it in one of the next examples. We will see why it is important that we know how to do this, because sometimes you need to do it. So -1 is cos pi plus I sine pi, which is brilliant. Let's check that it is actually true. Is it? So cos pi is -1, and sine pi is 0. So that's 0. So -1 plus 0. So it's true. Okay, so we've checked that it satisfies. Next one. The next one is -1 minus I root 3. So 3. It's -1 minus I root 3. So a quick sketch. Oh, yes, sorry. Sorry, of course. -1 can be written as 1 multiplied by, we don't need to write the 1, e minus I pi. And this is the sorry, there's no minus, I pi. This is the famous equality, Euler's identity. Oh yes, this is Euler's identity. The other one was Euler's formula. But yeah, that's E. This is beautiful because it contains all three major constants. There's pi, there's E, and there's I. And so the maths is all about these three numbers, and it's beautiful that all of them combine together and they make -1. Or you could do 2 pi I, and then it's going to be 1, which is also quite beautiful. But yeah, that's about it. And yeah, interestingly, let's just realize that if you square both sides, so it goes -1 squared is equal to e 2 I pi. What's e 2 I pi? Well, it's 2 pi, so it goes root 2 pi. That's a whole circle. That's 1. So it is, and it is 1 by all means. So yes, this one here we have -1 minus I root 3. So it's -1 and minus root 3. So that is here. And you draw a vector. And you can find that the modulus z is equal to, so z is equal to that. Modulus z is 1 plus 3. So 4 square root of 4 is 2. And argument z. So this is pi. And this is arctan root 3 over 1, which is 60 degrees. So it's 180 plus 60 degrees, which is 240 degrees, which is 4 pi over 3. And then we just write down that z can be written as 2, open bracket, cos 4 pi over 3 plus I sine 4 pi over 3. And another one that can be written 2 e I 4 pi over 3. That's it. Oh, I skipped number 3. So that was actually number 4. That's a problem of zooming. Zooming as in. Okay. So question 5. So question 5 is. Oh, let's do question 3. Actually, question 3 is quite small. So it's pi z is equal to pi over 4. So pi over 4 is just a number. It's a real number. So it's here, pi over 4. So modulus of z is pi over 4. And argument of z, what's the argument of z? Someone tell me. 0, yes, 0, or you can say 2 pi. Might as well be 2 pi. So z is equal to pi over 4, open bracket, cos 0 plus I sine 0, 0. Or you can write z is equal to pi over 4 e I multiplied by 0, which is true. I mean, it is really true. Z is, because e to the power I0 is 1, so it's pi over 4 times 1. It's true. And this is cos 0 is 1. So yeah. And finally, we have the 5th question. So 5th one. The 5th one is so z is equal to -2 plus 5i. And we have the modulus of z. Modulus of z is the square root of x squared plus y squared. Pythagoras theorem. It's the length of a vector. So it's square root of 4 plus 25. So which makes it square root of 29. And argument z, right, so it's -2. So it's -2 plus 5i, 5. So we need this angle. We need this angle. And we use, so it's going to be pi over 2 plus arctan. Why do I do this here? It's pi over 2, so it's 90 degrees. plus arctan 2/5. Arctan 2/5. So let's do that. Pi over 2. So pi over 2 plus arctan 2/5, which is 1.95, approximately 1.95. 0.95. And I mean, you could write it in exact form, but it's going to be too messy to do it in exact form. So I would write is that z is approximately equal to square root of 29, open bracket, cos 195 plus I sine 195, or z is approximately equal to square root of 29 e 1.95i. So I hope that makes sense. So this is just converting. Like, you need to really practice, because you really want to be confident in doing that. Solve simultaneous equations. So here we need to solve for x and y. Now, there are two different approaches. Like, if x and y were real, then this would be super easy. Yeah, actually, you would if x and y were real, you would only need one equation. Okay, so they don't tell us whether x and y. So, but suppose x and y are real, then the equation, then you only need one equation. Well, I mean, they won't be solvable because the x and y are not real. So 2 minus I, but I'll show you what to do if they were real. If we are in an imaginary world where x and y are real, equals 3 minus 6i. So what would you do? Well, you just open the brackets. So it's going to be 2x minus ix plus 3y plus 2iy equals 3 minus 6i. So what do we do next? Yeah, separate for real, for group real and imaginary, of course. So for real one, the real one is without the i's, yes. So it's 2x plus 3y equals 3. Imaginary is minus ix plus 2iy equals minus 6i. You drop the i's and it becomes minus x plus 2i equals minus 6. Now you have two equations, two unknowns. And if you solve them, you get a solution. But the problem is that the solution of the first equation will not be compatible with the solution of the second equation. And that's how we know that x and y are real. Right? So I hope you know how to solve equations. You could do, if you do the same with this second one, if you do find x and y, Do you mean why not I? Yes, of course, I mean why not I. Divide x and y. Do the same. Do the same with the second equation. Look at the nonsense result, and of course can rethink your life choices. Rethink your life choices. That means why did you think x and y were real? But they're not real, and that makes it harder. So anyone give me a way how to solve this now that we know that they are complex? So you can do substitution by all means. Let's look at the substitution. Like I've done it by substitution here. It took me about half a page. But you can see the horrible mess that I've made in solving this. And I try to be neat sometimes. The problem is because when you start doing substitution. So suppose we take the second one, and from the second one we write I minus 1 minus I x is equal to minus 1 plus 2 plus I y. And then you have x, which is equal to minus 1 plus iy on minus I. And then you substitute that into the first equation, and you do get a mess. It is solvable. I have done it. But let's imagine how you would do it without. How is there a way of doing it by what's it called, by elimination? Yeah, because that's what you want. Let the complex numbers of general form and then equate coefficients. But no, you can't do that actually. It depends. What do you mean? Let them be complex numbers of general form. That is general form, isn't it? What do you mean? Oh, exponential form. No, that wouldn't work because the exponents are not don't have the same power. Let x be a plus bi. Whoa. You get 4 equations. You get 4 equations and they are solvable. But I'm thinking well, I've done it by substitution. Like I've honestly done it, and it's took me half a page. You could do it. I think we can do it by elimination. So this is by substitution. And you know how to do it. I mean, you carry on doing it. It will be horrible-ish. Let's do by elimination. And you can't do by elimination with complex coefficients because it doesn't work. But you can do elimination with real coefficients. So we want to make the coefficients real for by elimination. Let's make the coefficients for x real. Okay. And to make this real, we need to multiply by the conjugate, by the complex conjugate. So the first equation, we're going to multiply by 2 plus I. And this second equation, we're going to multiply by 1 plus I. You see what I'm doing here? If I multiply this by 2 plus I get a real number. If I multiply this by 1 plus I get a real number. So let's have a look. Let's. I'm excited. So it's going to be 2 minus I multiplied by 2 plus I, x plus 2 plus I multiplied by 3 plus 2I, y equals 3 minus 6I multiplied by 2 plus I. And the second equation, I'll do it straight away. So it's going to be 1 minus I, 1 plus I, x minus 2 plus I multiplied by 1 plus I, y equals minus 1 minus I. Add x to the second equations to both sides. That won't work because you then now you have a stray x on the right hand side, which doesn't help you. So here you open the brackets. So let's do this. So 2 minus I, 2 plus I. If you don't know what it is, just open the brackets and see what it is. It's going to be 4 plus 1, so it's going to be 5x plus, we open this, so it's going to be 6 plus 4I plus 3I minus 2y equals, open this, so going to be 6 plus 3I minus 12I minus 6I squared, which is plus 6. So the second equation, 1 minus I, so it's going to be 2x plus, so that's going to be 2 plus 2I. Oh, that's a minus. Ooh. What are we going to do about it? Let's just do it like this for now. Leave it as minus 2 minus 2I plus plus I minus 1. Okay, equals minus 1 minus I. Okay, beautiful. Simplify. So 5x plus, so that's 4 plus 7I, y is equal to 12 minus 9I. And this is going to be 2x. And this is going to be minus 1 plus 3I, y equals minus 1 minus I. So to eliminate them, I'm going to multiply the first one by 2 and the second one by minus 5. Okay, so I get 10x plus 2 open bracket 4 plus 7I y. You notice how I'm not opening the brackets, I don't want to. And it's going to be 24 minus 18I. Very carefully, so 2x times minus 5, so minus 10x plus 5, 1 plus 3I y equals, so minus 5, so 5 plus 5I. Now, I mean, it's not the fastest method, but this is super elegant. Now I eliminate. Okay. So adding this, there's going to be 8 plus 14i plus 5 plus 15i. And this is multiplied by y. And that's equal to 29 minus 13i. Ooh. It still looks scary. And it's 13 plus 29i. 29iy equals 29 minus 13i. Can someone guess what y is? Look at the numbers. Oh, wow, beautiful. Halil, how did you do that? How did you guess? How did you guess this? And Tony, how did you guess? Well done. Did you actually guess, or did you do the division? Well, y is going to be minus I. Because indeed, if you multiply this by minus I, that's what you get. You get minus 13i plus 29i times minus I, which gives you plus 29. So that is true. So how do we do this? Well, do we divide? So, okay, so y is equal to, well, yes, but yes, I squared is minus 1, but it's still, I mean, it wasn't obvious to me at first. I mean, I did division. 29 minus 13i divided by 13 plus 29i. So what you do is you multiply the top and bottom by the conjugate, by the complex conjugate. So you get 13 minus 29i, and here you multiply by 13 minus 29i. And then you get, on the bottom, you get 13 squared plus 29 squared. And here you get 29 times 13. Oh, that's a big number. So 29 times 13 minus 29 squared I minus 13 squared I, and then plus minus 29 times 13. 29 times 13 cancel, and you are left with minus I, open bracket, 29 squared plus 13 squared, divided by 13 squared plus 29 squared, which gives you minus I, which is beautiful. It's like, all right, so we found out y, and now we need to take any equation to find x. And I'm gonna go with the easiest one. I'm gonna go with this one. I'm gonna go with this equation. It doesn't have to be an equation from the beginning, because the equations in the beginning are scary. I don't like them. So I can find x now from here. So from here, we put y equals minus I. Let's use a different color. Minus y, so that makes it 2x. So y is minus I, so it's plus I. Okay, I don't want to. Let's not try to over clever yourself. myself. So 3i minus I, and that's equal to -1 minus I. So 2x minus I. So minus 3i squared. So that's plus 3 minus 3. So minus 3. That's wrong. It's in. How do I know this is wrong? So I've made a mistake, obviously, and I hope you can see that my mistake. How do I know I've made a mistake? So this is my my mechanism, how I check myself. Okay, so what do? I see, well, I see here that 1 and 3, they are both positive. So positive, positive. So when I open the brackets, they either have to be both positive or both negative in the normal scenario. But we are multiplying by I, therefore, when I open the brackets, I either have to have plus minus or minus plus. So I see minus minus and I'm not satisfied with this. Do you understand what I'm talking about? If you have a bracket, let's say x plus y, you can see they're both positive. So if you multiply by whatever it is, so whatever, is going to be either positive positive or it's going to be negative negative. However, with complex numbers, because we are multiplying by y, the plus plus have to change either to plus minus or minus plus, depending on what it is. And I see minus minus, I'm not satisfied. That I made a mistake, and obviously I made a mistake, and it's here. So it's plus I. So I forgot the double minus, so minus minus, so it's plus I, minus 3. So now I'm happy. I'm happy because they're different signs. This is one of the ways I check myself for errors. Equals -1 minus I, so that makes it 2x is equal to 2 plus minus 2i. So x is 1 minus I. That's it. So yeah, it's a complicated one. Probably the hardest question today. Except for 4-1. We're gonna skip 4-1 because it's horrible. It doesn't help understanding. Wait, are we done? Oh, wait a second. Have we skipped something? Oh yes, we have skipped something. And let me just make this smaller. Hopefully it's still readable. Yeah, it is. And find the following. Now, yeah, the first one here is quite nasty. So I'm gonna skip number 1, and I'm gonna go straight to number 2. So, does anyone know how to do this? If there are simultaneous equations with no solution, which also don't have imaginary coefficients, is there any partial solution? How do you find it? No, simultaneous equations. Simultaneous equations. Well, let's see. Let's create a simultaneous equation with complex coefficients. So x plus I so x let's make it 1 plus I x plus I y is equal to 7. I'm pretty sure this doesn't have a solution. It is imaginary coefficients, and I'm not 100% sure, but you can explore. But I'm like 99.9% sure that this doesn't have a solution. So I'd say simultaneous equations with complex coefficients don't have to have a solution. It's the same. Yeah, like that. Okay, so, Benjamin, thank you. So Pratham said binomial expansion. Yes, you could do binomial expansion. It's not the most optimal way, but Benjamin said, brilliant. Yes, you do trigonometric form, or you can do it in modulus argument form, which is even better. So you could do a binomial. So 2 binomial. It's going to be quite big, and you need to remember all these coefficients, like 6 choose 3, 6 choose 4, 6 choose 5, which is not the easiest thing in the world, but you can do it. Or you use the modulus argument. And this is where modulus argument is so powerful. Just look what happens. So z is equal to 1 plus I root 3. So modulus of z is 2, and argument of z, all right, what is argument of z? So it's 1 root 3, 1 plus root 3. So if you draw this vector, what's the angle? Pi over 3. Yes, of course, pi over 3. So this is arctan square root of 3 over 1, which is equal to pi over 3. Does everyone understand this? Does everyone understand? Is there anyone who's not confident with this? Please let me know. Okay. Okay, so if you do the modulus argument form, look at this beautiful thing. So because this can be written, z can be written as 2 multiplied by e to the power I pi over 3. And now z to the power 6, which is what we have, is 2e to the power I pi over 3 to the power 6, which gives us 2 to the power 6 multiplied by e to the power I 2 pi. And what is this? It's so this is 64 e I 2 pi. And if we remember 2 pi, that's there. It's 1. It's so 64. 64. Wait a sec. So the answer is that 1 plus I root 3 to the power of 6 is 64, right? We're happy with that. But does that mean do you know where I'm going with this? What? Yes, Yelena, I am that is true. Absolutely. I 1 plus I root 3 is not 2. So the thing is that the 6th root of 64 has many values. So when you talk about complex numbers, the root has multiple values. Unlike in real numbers, square root is always a single value. So in real numbers, square root of 25 is 5. Yes, we don't argue with that. It's true. Square root of 25 is some people, especially in the States, they like that. They say plus minus 5, which opens a whole different can of worms. So we define the square root as a function, and function can only have one value. Remember, functions can only be 1 to 1, or they can be many to 1. They're never 1 to many. So the square root of 25 cannot be two different numbers in real numbers, but in complex numbers, the square root has multiple values. And this is very important. So the 6th root of 64, and we will show this in exercise 4, has several roots. The 6th root of 64 has several values. They are called roots of unity. They are, but don't need to call them that. It's square root of 64 has different values, and one of these values is 1 plus I root 3. When we have shown that 1 plus I root 3 is in fact 2. Let's confirm that. I'll use Wolfram alpha. So it's going to be 1 plus I multiplied by square root 3 to the power of 6. And the result is 64. Look at that. 1 plus I root 3 is to the power of 6 is 64. There's no doubt about it. Well, unless I am wrong and Wolfram alpha is wrong. It has 6 values. That is true. Yes, Martha. Thank you. We will show that in a bit. So yes, that's a beautiful result. That's a beautiful result. Okay, so let's do another one. Let's do another one. Why did I lock them? I always do that. Okay, so I'm going to do question 3. How much time do we have? Okay, we should be able to do it. So I'll quickly skim through question 3. So let's choose a different color, brown. So 3, f of z is equal to z minus 1 to the power 5 plus 1 over z minus 3. And we know that z is 1 plus 2i, so it's going to be, well, it's a function, so f of 1 plus 2i is 1 plus 2i minus 1 to the power 5 plus 1 over 1 plus 2i minus 3. What? Yes, minus 3. So I'm not making. If I make a mistake, please let me know. So 1 cancels, and it's going to be 2i to the power 5. So it's going to be 2 to the power 5 and I to the power 5. And an interesting thing, so I is I squared is minus 1, I cubed is minus I to the power 4, I to the power 4 is 1, and I to the power 5 is just I. So so plus 1 over 2i minus 2. So 2 to the power 5 is 32 times I to the power 5. So 32i plus. Now this one, we need to multiply top and bottom by 2 minus 2 minus 2i. And this is minus 2 plus 2i minus 2 minus 2i. So we will multiply by the complex conjugate, and we get 32i minus, so that is 4. So it's minus 1 minus 1 half minus 1 half I. I believe this is to be true. No, I'm wrong. This is not 4. This is 8. This is 8 because that's 4 plus 4. Yeah, that's 8. So that's going to be a quarter. So it's a quarter and a quarter. And that gives us minus a quarter plus 127 quarters I. This is just a simplification. So yeah, don't worry if you don't see it right away. See for yourself in the future. Okay, problem 4. So here we got to the interesting part. This is like this is what we came here for. We want to find the 4th root of 1. So as I said, we're going to skip the first one. It's too messy. It's not hard, it's messy. So 4th root of minus 1. So 4th root of minus 1. In other words, equal to z. That means minus 1. So sorry, that also means that z to the power 4 is equal to minus 1. Sorry, I'm talking rubbish. No. Minus 1, so 4, so 4th root of minus 1 is minus 1 to the power a quarter. Yes, that's how you do it. And then we remember that minus 1 is e to the power I pi. But that's not the only possibility. It could also it is actually e pi plus 2 pi n. because -1 is e to the power I pi, but it is also e I 3 pi. It's also I 5 pi. Oh, sorry, not 3 pi. 1, 2. Oh yes, 5 pi. E I 7 pi. So etc. In we can write this as E I pi plus 2 pi n, where n is a whole is an integer, is any integer. Does that make sense? Does everyone understand this? So -1 can be written like this. Just like 1 can be written as e to the power I0, it also could be written as e I 2 pi. It also could be written as e I 4 pi equals etc. And in total, it could be written as e I 0 plus 2 pi n, where n is any integer, in any integer value. Is there anyone here who's confused with this? Is there anyone? Oh, there's only 17 people left. It might be I have confused a lot of you. I think it was like 30 people in the beginning, and it scared off half of you. Hopefully not. Okay, so what all we need to do is just chuck that in and look at this beauty. It becomes e to the power I pi plus 2 pi n to the power a quarter. And then we open the brackets, so it's e I pi over 4 plus 2 pi n over 4, which is pi n over 2. And that's it. So now we just need to plug in different values of n. So we try n equals 0, n equals 1, n equals 2, n equals 3. So 0, and this is z. This is going to be e I pi over 4, which is square root of 2 over 2 plus I square root of 2 over 2. If n equals 1, we plug that in. So it's going to be e I 3 pi over 4, which is the same as minus root 2 on 2 plus I root 2 on 2. When it's 2, so e I 5 pi on 4 equals, so that's 1, 2, 3. So it's minus square root of 2 over 2 minus I root 2 over 2. And e I 7 pi over 4 equals root 2 over 2 minus I root 2 over 2. So these are the 4 different values of the fourth root of -1. So these numbers are all equal to fourth root of -1. Can you use the idea for real numbers to the power of complex numbers? Real numbers to the power of complex numbers, of course. So if you have 4 to the power I, that is 4, which is 4e I 2 pi. We put it to the power I. Oh. Oh yeah, because if you do use n equals 4, you won't repeat it. You won't repeat a solution. You'll get the same. For n equals 4, it will be e to the power I 9 pi over 4, which is square root of 2 over 2 plus I root 2 over 2. So it repeats. You get the same result as here. Do try to prove that. 4i. Oh no, sorry. No, sorry. I don't. Um, I don't have the mental capacity to remember how to do this. Sorry. I'll need to look it up. It might be something simple. It's just yeah. So 4 to the power I. It's something to explore. Don't remember doing this. Like an interesting task is to do. Oh, what is I to the power I? I'm sure I've done it at some point. I to the power I. Or 4 to the power I. Something to explore. ln 4i. E ln 4i. Oh yeah, that's a complex number. Oh no, but well, we don't know. It's a complex number, so it's going to be. Does that work? Ln 4. What is ln 4? Ln 4 is just over 1, so it's approximately 1, so it's somewhere here. Let's do 4 to the power of I. Yeah, it looks like a number. It's a complex number, which is 0.1 plus 0.9. So that sounds about right. 0.1 plus 0.9 I. Yeah, actually, thank you, Andre. That's brilliant. So simple. Not a very difficult solution. And this one would probably harder. Solve the quadratic equation. So here, oh wait a second. We haven't finished. So 8. Well, I'll just show you how to do this. So 8 is going to be 2e to the power 0 plus 2 pi n I, and this is to the power of 1/3. So you get two different values for n equals 1, n equals 2, n equals 3. Yeah, remember n equals 0, n equals 1, n equals 2. So you get 3 different values of this. So sorry, 8. Yes. So it's going to be 2 multiplied by, so it's going to be 2. So it's going to be 2 multiplied by e I 2 pi over 3. And it's going to be 2ei 4 pi over 3. So 3 values. Okay, so that's for this one. For this one, it's going to be 8 minus 6i. So it's going to be Oh yeah, so I haven't done this one, but it's the same principle. You write down modulus of z, which is 10, as a matter of fact. So it's going to be 10 multiplied by e I theta plus 2 pi n, and then you take it to the power 1/2, and that gives you the two values. Okay, and this you need to simplify that first and then do the same. So this is the power of this one. So solve the quadratic equation. So this is just using the discriminant, just something discriminant formula. So it's b squared minus 4ac. So it's going to be 1 minus 2i squared minus 4 times minus 2i, which gives you 1 minus 4i minus 4 and plus 8i, which is 1 plus 4i minus 4. And if you notice, if you're really attentive, if you look at this, this was 1 minus 2i, and this is 1 plus 2i squared. Yeah, do you see that? Because this was 1 minus 2i squared, and this is 1 plus 2i. So this is 1 plus 2i squared. And then we can use that to solve the equation. So Z1, the first solution, is minus 1 plus 2i minus 1 minus 2i over 2, which gives us minus 1. And the second solution is minus 1 plus 2i plus 1 plus 2i over 2, which gives us 4i over 2. That's 2i. Okay, and I don't know if I should be showing you this, but yes, you can do this. Solve z squared plus 1 minus 2i z minus 2i equals 0. And the solutions are minus 1 and 2i. Vraiment. Okay. Finally, we get some Argand diagrams and sketch the region that satisfies the following relations. So we know that the modulus of z is the distance from 0. And modulus z minus a is the distance from a. Therefore, looking at question 1, this is the distance from the point 3i. So z minus 3i. So this is the distance from 3i. And it's greater or equal to 3. Okay, so if we draw the diagram, so we have, so this is 1. If we draw the diagram, so there's 3i, and the distance is great. If the distance from this point is greater than 3, so greater or equal to 3, so it's a circle. It's a circle, and we need everything that is beyond this circle. So we shade the region. So the shaded region, including the circle, is the points where z minus 3i is greater than 3, or equal than 3. The second one, so the second one is quite easy actually. So real value of z plus the imaginary value of z equals 1. Well, what is the real value of z? Well, if z is written as z is equal to x plus iy, then the real value of z is equal to x, and the imaginary value of z is y. So in effect, so it's actually what it says, that x plus y equals 1. And that's a straight line, and I don't think I need to draw it. So it's a straight line. Straight line. Going back to this one. You can actually prove this algebraically. So let's say we have z is equal to x plus iy. So we have x plus iy minus 3i is greater than 3. So this is modulus of x plus y minus 3 greater or equal to than 3. And the modulus of z is square root of the real part plus the imaginary part. That's 3 squared, greater or equal than 3. And we just square both sides, so x squared plus y minus 3 squared, greater or equal to 9. And that's the equation of a circle. Equation of a circle. Well, of course, it's an equation on a circle on the left, which is greater than 9. So the equation of the outside of a circle, of the outside of a circle, I don't know how to do this, to say this in English properly. It's the equation of the. It's not an equation. It's an inequality. It's an inequality which describes the outside of a circle on a complex plane. So English it up a bit. Let's do the rest. And 3, I was like super excited doing 3. I was like, whoa, that's cool. Because 3, let's read what it says. It's modulus z minus 2i plus modulus z plus 2i, and that is equal to 8. So what on earth is this? Well, this is the distance. So the first bit is the distance from 2i. Distance from 2i. And similarly, this is the distance from minus 2i. Distance from minus 2i. So let's sketch that. So bam, bam. So 1, 2. Let's make this 2i. And this is minus 2i. So we need all the points where the distance. That's a good idea, Martha, but unfortunately it is not. A perpendicular bisector would be if you had equal between them, like this. That would be a perpendicular bisector, but this is not that. The total. So we have a point. Let's have z, and we know that the distance to that and the distance to that, a, b. So a plus b equals constant. What is the name of the shape? Oh, you're getting close, Martha. Very close. This the total of the distance from two given points is a constant. What shape gives us this rule? What shape gives us this rule? Something to do with space and planets. Well, oval is not a proper name of the shape. An ellipse, Paris. Yes, it is an ellipse, of course. In an ellipse, you have two focal points. You have two focal points, and any point from at the ellipse. That's the definition of an ellipse. So any point, so F1, F2, for an ellipse at A F1 plus A F2 is constant. That's the definition of an ellipse. So yes, it is an ellipse, and all we need is to find the so it's 8. So let's say, what's the point? It's going to be 4i, I believe. So 4i, if you take 4i, that's 4 and 2, that's 6, and plus 2, yes, 4i. And then it's going to be minus 4i. Now here is going to be something like 4 and 4, so that's 2 and 2. So this is 2, 4, so slightly less than that. So here 2, 4 is going to be slightly less than that. So 2, 4, slightly less than that, less than that. So beautiful. So it is an ellipse. Cool. It is an ellipse is a stretched circle. I'm not sure about that. Oh, oh yes, yes. An ellipse is a stretched circle, by all means, of course. I agree with that. It is stretched along the x-axis, yes. A circle is an ellipse when the foci are together. Yes, that is correct. The foci. Okay. And the last one, yeah, the last one is simple. It's a perpendicular bisector. So it's a perpendicular bisector of the 2 points. So that's the distance from 2i and the distance from minus 2i. So question 4. So z minus 2i is equal to z plus 2i. And so we have the same points. We have 2i, and then 2i, and it's a perpendicular bisector of the two. Oh, wait a second. Why did no one correct me? Two eyes here. That's embarrassing. That's embarrassing. So minus 2i, 2i. It's shame on me, but it's shame on you guys too. 4i minus 4i. So this is x and this is iy. Okay. Right. And here, so we all make mistakes. So let's make this 2i, and this is minus 2i. And on the perpendicular bisector is just the x-axis in this case. So basically, the equation of this line is y equals 0. Let's see if that actually gives us the same result. So we got modulus of x plus iy minus 2i is equal to modulus of x plus iy plus 2i. Well, the modulus of this is x squared plus y minus 2 squared equals x squared plus y plus 2 squared. Of course, there's a square root, but we can ignore that. So open the bracket, so x squared plus y squared minus 4y plus 4 equals x squared plus y squared plus 4y plus 4. Bam, 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 bam. So it's going to be 8y equals 0, y equals 0. Yes, it gives us the y, which is the same as the x-axis. What if you had 3 foci? Ooh. I'm not sure you can have 3 foci. Sort of like an egg. 3 foci. Can you have 3 foci? What's the definition then? If it has 3 foci, what's the definition of the shape? Okay. Excellent. Let's finish here. So I hope this was useful, and I'll see you all next week. Next week we are doing circular motion again, and yes, so enjoy and have a great week. Welcome. See you all.